on the board. So let's start with the first one. What does it mean to square something?
Multiply it by itself.
There we go. You multiply it by itself. So what does it mean to square root something?
The opposite of that.
Well, that's true, Matthew. Do the opposite of that. What would be a specific verbalization you would use? Like, let's say there was an alien come down to the planet, and you wanted to describe to this alien who's never done square roots before, okay? Never. And you said, the square root of 81 is 9. And the alien's like, boop, boop, beep, bop, why? Like, why? What do you even mean by a square root? What are you talking about? So who'd like to try that? What would you tell them about what that is? Beep, beep, boop, bop. Anyone want to try? Chris?
Well, how I figured it out is take 81 and then like exponent to parentheses 1 divided by 2.
Oh, okay, sure. You can type it into the calculator and that would tell it to you, right? Very good. Yeah. So we have this device called a calculator, and the alien would be like, all right, well, why does that mean anything? I mean, so what? You have a device. Yeah, dig it.
So I'll explain to him what squaring is, and then I'll say that square root is just like the opposite, where you want to see what number divided equally. So you only get one number and not a decimal or a fraction.
That's true. That's true. Okay, you're so close there to the definition of square root. You would explain what squaring is first, and then you would say to square root 81 means to find what? A number times itself that equals 81. Yeah, there you go. So when you square root a number, you're saying what number squared equals that number, and that would be the definition. You would say, well, a square root means you look at that number and you say, what number can I multiply times itself to equal 81? And that number is 9. And then the alien would say, okay, thank you. Let's go have some pizza. All right, how would you describe the shape of a parabola? And maybe I'll just pull one up here real quick. Here's x squared, and I can do something to it there. So how would you describe the shape of a parabola? Notice that if I zoom out, what does it look like?
A comet?
Oh, maybe like a comet? That's interesting. If I zoom out, it looks like a really, really, really tall, skinny U. What happens if I zoom in? If I zoom in, does it look tall and skinny anymore? All I'm doing is zooming in. Does it look tall and skinny anymore? No. So it depends on your perspective, huh? If you're far, far away, it might look tall and skinny. But if you're really up close, it might look wide. But no matter what, whether you're far away or close up, what does it look like? A what?
A U.
A U, right? It looks like a U. Even though that's probably not how any of us make a U. Probably we make a U, well, okay, not like that. Like that. Yeah, so a U is technically a little wider down at the bottom than, say, a parabola is. A parabola comes down to a finer point than a U does, which is typically a little wider at the bottom. Anyway, it looks like a U. What other characteristics does a parabola have? For instance, does it have any symmetry?
Yep.
Where is the symmetry? Yeah, down the middle. So if you folded that piece of paper in half, you would get the same picture on both the right and the left-hand side. It's right-left symmetric, or you could say there's a mirror image line, a mirror, that goes right down the middle, and what you see on the right is what you see on the left. So every parabola is going to be symmetric. All right. And then how about my last question here? What is the etymology of the word quadratic? I feel like maybe we've talked about this one before. I know we've done some etymologies. What's the etymology of quadratic? What are we more interested in, the quadra or the attic? And a quadra. What other words start with quadra?
Quadriplegic.
Quadriplegic. That's someone who no longer has the ability to move their arms or their legs. What other words?
Quadrate.
Quadrate? What is that? I don't even know it.
I don't know, but I Googled it.
Actually, quadrate is a verb form, ATE, the verb, which means to make something square. So my entire childhood quadrated me. right? That's just a joke. It made me square. Okay. Yeah, to quadrate something is to make it square. Much like if you were going to put a picture frame on the wall and you wanted to square it up, maybe that's what it would mean. Okay, what's another word that starts with quadrilateral? And what is a quadrilateral? It's anything with 4 sides, right? Okay, any other words with quadra? What is it? Oh, quadruplets, great. When you're lucky enough to have 4 kids all at once. Yep, so what does quadra mean, folks? It kind of means 4. It kind of means 4. If you look up the etymology of quadra, part of the definition of quadra will say 4, but there's another really more important etymology of the word quadra that means something else. Does anyone know? So we haven't talked about it before? Yeah, it means square. Quadra actually means square. Now, that makes a lot of sense because even though most words quadra means 4, like quadrilateral is 4-sided, quadriplegic, they don't have 4 limbs, quadruplets is 4 babies. Quadratic, if you look at the general quadratic equation, ax squared plus bx plus c, what about that indicates a 4? Is there anything in there that means 4? Nothing at all. There's nothing about that that suggests the number 4. Rather, is there anything in there that suggests a square?
Yep.
Which?
The exponent.
Yeah, the exponent. That's a square. Because whenever we say x to the power of 2, we actually say x squared. And why do we say x squared? We did this before, I think, weeks ago. Why do we say x squared instead of x to the power of 2? Because of a 2D, 3D thing, that's exactly right. Because if you want to find the area of a square, the area of a square is length times width, but in the case of a square, they're the same measurement. So it's just, let's say that the side length is x and that's x. Then it's x times x, which is x to the power of 2. So mathematically, culturally, over history, people, instead of saying x to the power of 2, x to the power of 2, x to the power of 2, that's so lame, they finally just said x squared. Meaning, if you took a piece of wood that was x inches long, and then you wanted to build a square out of it, then that's what you would be doing. I'm sorry, this is supposed to be a piece of wood. The point is you're making a square literally out of 4 pieces of wood that are x inches long, then that would be x squared. You're using x and you're building a square out of it. And so the area of that square would be x squared. So historically, that's why we refer to it as x squared. So right here, that is where we get the name quadratic. This is a quadratic equation because it has an x squared term in it. Now, what if you cover up the x squared term? What's that equation? Yeah, that's just a line. You might not recognize it with the b and the c, but you'll recognize it with mx plus b. So really, this is the linear component, and this is the quadratic component. So every quadratic equation that we work with, ax squared plus bx plus c, has a quadratic piece and a linear piece. But the whole thing together is a quadratic equation. And we call it quadratic because of the x squared. If you got rid of the x squared, it wouldn't be a quadratic anymore. It would be a linear equation. Okay, well, folks, that's quadratic. So what about parabola? Well, parabola doesn't necessarily have a fun etymology. The word parabola, if you look down here, means placing side by side or to throw beside. Not quite sure on that one, why we refer to that as a parabola. But have you ever heard of conic sections? This is kind of fun. Well, conic sections, you may or may not have studied them in high school. If you take a cone, like a birthday hat, but instead make it 3D and solid, like a cake. So I want you to all imagine that this is a 3-dimensional cone cake. First of all, would you be excited
Yes.
if for your birthday you got a cone cake?
Yes.
I think that'd be pretty cool, a cone cake. Watch what happens when you slice the cake in different ways. If you slice the top off of the cake, what is the cross section? It's a circle. So your piece of cake would have a circle on the bottom if you just cut off the top. But then what if you cut the cake at an angle? Not a big angle, just a little angle. What would the bottom of your piece of cake look like? An ellipse. And now, what if you cut the cake parallel to the side of the cake? So you literally cut the cake at the same angle that the side of the cone is. What would the bottom of your cake look like? A parabola, which is pretty cool. And then what if you cut the cake straight up and down? Just straight up and down along the edge of the cone. that would make a hyperbola. So we call these conic sections because literally the cross sections of a cone will give you a circle, ellipse, parabola, and hyperbola depending on the angle that you cut. So which one are we talking about? The parabola. We're talking about the parabola. It what?
I would say if you cut it like that, would it just fall down?
Well, the K would fall apart like that, but it would be neat for a minute. Okay, so quadratic, as I said, comes from down here at the bottom, 17th century French quadratique, or quadraticus, or quadratus, to made square. So if you look at the etymology, it's made square. It doesn't say anything about the number 4. Okay, well, here we go, folks. We're starting today to learn about chapter 10. This is our last chapter. I know everyone's very sad. Everyone's very sad. Did we already talk about signing a petition to extend the course through summer? Okay, I actually had 5 of you sign it. So if the rest of you want to sign the petition after class today, we can get the ball rolling. Anyway. All right, well, we're going to do chapter 10. We have 4 days to do chapter 10, and then a test, and then we'll have a whole final exam review day in which I give you a practice final, and then we'll take the actual final exam. About chapter 10, just so you know, I'm gone all next week. I really regret that I have to be, but I do have to be, and so I won't be here those 2 days. I will be back by Thursday, so if you wanted to swing by my office on Thursday, I'll be here, and you could ask me any questions you like. Also, I have your test available for pickup. I don't have your test to get back to you today, but for instance, if you wanted to come get it next Thursday, you could. And so on these 2 days, you'll have a teacher here by the name of, I think it's Larry Dieter. Did I already say that?
Yep.
Larry, okay. So I'm saying a lot of things I've already said. Larry Dieter will be here over the next, all of next week, those 2 class periods, to walk you through the material in chapter 10. Keep in mind, I'm going to give you a PDF copy of the whole chapter 10 notes filled out. That is, except for the first couple pages, because we're about to do it today. So believe it or not, last night, you're not even going to believe me when I say this, it's too good to make up. Last night, my wife and I watched Labyrinth with David Bowie. Have any of you seen that? Mm-hmm. It is a fantastic movie made in 1986. All right, so we watched Labyrinth, and you know what I did while I watched Labyrinth? I filled out this entire packet. Do you know why? Because I love and care about you. I sat at home last night and watched Labyrinth while filling out this entire packet so that I could give it to you. I'll send it to you as a PDF, and that way you'll be able to look through all the notes. Okay, so that's chapter 10. That's what's coming up. All of chapter 10 is about quadratic equations, ax squared plus bx plus c. Did I already tell you the Snoop Dogg joke? I didn't? Did I tell you the knock knock joke? You get both today. Maybe I didn't tell you a joke on test day, because Monday was the test. Here's my first joke. Why does Snoop Dogg carry an umbrella? What?
This is random problems.
Well, that could be the ending to the joke. It's not this particular joke. Why does Snoop Dogg carry an umbrella? For drizzle. That was good. That was some real laughter there. Okay, knock, knock. Now everybody has to respond. Knock, knock.
Who's there?
To. Actually, it's to whom? More real laughter. This is amazing. All right. So, warm-up material. What does it mean to solve a quadratic equation? These are the 2 big questions we're talking about today. And I hope that when you walk out of here, you would be able to tell anyone what it means to solve a quadratic equation. So that's my first question for you. What does it mean to solve a quadratic equation? I'll start by just asking, what does it mean to solve an equation? So let's say I gave you 5x plus 3 equals 13. What does it mean to solve this equation? Solve for x, what does that mean? To get x by itself, what does that mean?
It means to find a number that goes into 5x plus 3 that equals 13.
Right, we're looking for a number. To solve for x and getting x by itself means to find a number that I can plug into this that'll actually make it equal 13, which will make the statement true. So that's what it means to solve an equation. Solving for x, getting x by itself, all these things all mean find a number you can plug in to make the statement true. So any definition of solving an equation better have the word true in it, right? Because we're talking about true, not false. So that's what it means to solve any equation. So what does it mean to solve a quadratic equation? What does it mean to solve a quadratic equation? To find a number
we can plug into the equation Make it true.
There we go. To find a number that you can plug into the equation to make it true. Now, how many numbers will there be for this one? There's only one solution. How many are there here?
2.
Yeah, maybe 2. It could be 2, it could be 1, it could be 0. Now, that's pretty weird to think about. But it's at most 2. So that's one definition. Everybody at the top of your chapter 10. Right up here at the top of chapter 10, let's go ahead and start writing some notes. Just real quick, 2 statements. The question is, what does it mean to solve a quadratic equation? The answer will be the same, even if it wasn't quadratic. This is going to be the same answer for any equation, but we're specifically talking about quadratics today. So what does it mean to solve a quadratic equation? 1, to find the numbers that plug in to make it true. So that's just part of the definition. There's a second part to it. Solving any equation means finding a number to plug into the equation that makes it true. But there's another part. So I'll give you an example. I'll make it an easy one. X squared plus 7x, actually I'll make it minus 7x, plus 12 equals 0. What numbers do I have to plug in to make that equation true? I'm assuming you're all trying to factor it. What multiplies to make 12 that adds to make negative 7? Is it negative 3, negative 4? And then by the 0 product rule, this times this equals 0. So either x minus 3 equals 0 or x minus 4 equals 0, which means x equals 3 or 4. So 3 and 4 are the only numbers in the universe that you can plug into that equation to make it true. Might as well check. What if I plug in 3? 3 squared is 9, minus 7 times 3 is 21, plus 12. 9 minus 21 is negative 12, and negative 12 plus 12 is 0. So that worked. What about 4? If I plug in 4, 4 squared is 16, minus 7 times 4 is 28, plus 12. 16 minus 28 is negative 12, and negative 12 plus 12 is 0. Okay, so did we just do it? Did we just solve the quadratic equation? Yes, we did. That is for sure a solution. Now, look at the parabola x squared minus 7x plus 12. What do you notice about this parabola? What? Who said that?
I said it hits 3 and 4.
Yeah, it hits 3 and 4. What specifically is 3 and 4? There you said it. What? The x-intercepts. And that's the second part of the definition. To find the numbers that plug in to make it true, which are the x-intercepts? So, those two things always go hand in hand. If someone says, what does it mean to solve an equation? You would really say, find the numbers to plug in to make it true, which will also be the x-intercepts. So even that graph I just showed you I didn't even solve it, but I put up 5x plus 3, whatever. Here, that was this equation, 5x plus 3 equals 13. What's the x-intercept? 2. And is that the answer? 5 times 2 plus 3? Yeah, so that'll always be the case, folks. Any equation at all, if you graph it, the x-intercept will be the solution to that equation. Isn't that cool? Have we talked about that in here? We have a little? That x-intercepts are the answers? Okay, maybe we have a little. Okay. Well, so that's the first question. What does it mean to solve an equation? To find the numbers you can plug in to make it true, which are the x-intercepts. And then the second question is, what are imaginary numbers? Who in here already knows what an imaginary number is? What is an imaginary number, Jasmine? Yeah, a negative inside a square root. Everyone, if you have your calculator out handy, go ahead and calculate the square root of -1 and just see what you get. What does your calculator say to you? Error, non-real answer. Anything else? Did anyone get any other messages from the calculator?
Domain error.
Domain error. What else? Oh, your calculator's fancy. It actually told you I. Okay. Well, you can't square root of -1. And I like this answer the best, non-real, because the answer to this question is not on the number line. Okay? Imagine a number line. This is just your normal, everyday, run-of-the-mill number line. Every number in the universe is on this number line, right? 37 is on this number line. -100 is on this number line. All real numbers are on this number line. Well, is the square root of -1 on that number line? Where would I put it? Like pi, I could pretty easily place pi on here. I would just put pi right here, right? Roughly there, 3.14. Could I put could I put the square root of -1 on here somewhere? The fact is, no, the answer to this problem is not on this number line. There is no real number that is equal to the square root of -1. There's no real number that's equal to the square root of -1. So it's not on the number line. We're going to see that here in a second. So whenever you square root a negative number, it really is an error or a non-real or a domain error because there literally is no number on the number line that's equal to that. And I'll give you a quick proof. Let's just say that the square root of -1 really was equal to a number. Let's say it really was. It really is equal to some number x. Then I would do a little algebra right here, and I would square both sides. And I would say, now this side, what happens when I square a square root? They cancel. So I get -1 equals x squared. Well, is that even possible? Is that possible that I can take a number and multiply it by itself and equal a -1? I mean, that's not even possible. If you take any number at all, something times something, let's say that that number was 0. 0 times 0 would be 0. That's obviously not -1. If I took a positive times a positive, what would that be equal to? And if I took a negative times a negative, what would that be equal to? Positive. So there is no way to take an actual real number from the number line and multiply it times itself to equal -1. It's just impossible. Okay, it literally is impossible. And that's why they say it's a non-real number, because there is no number on the number line that I can square to get -1. Therefore, there is no number on the number line that's equal to the square root of -1. Anyway, it turns out that even though the square root of -1 does not equal anything, we use it a lot in mathematics, and that's what we're going to talk about today. So, everyone, will you take out this sheet called Introduction to Quadratics? All right, I can't write on the whiteboard or over there, but I'll just write my answers up on here. So, what is a linear equation? Or I should say, what is the linear equation? Yeah, y equals mx plus b. And why do we call it linear? Yeah, when you graph it, it's a straight line. So you just get some sort of straight line. So that's a linear equation, and we use the word linear because it's the word line with the letters AR at the end. So then what's a quadratic equation? It's ax squared plus bx plus c. And why do we use the word quadratic? Yeah, because quadra means square, and we're referring to this term right here. This is the term. This is technically called the quadratic term. Because this is the linear component. So when we talk about a quadratic equation, we're really referring to the ax squared part, because if that ax squared part wasn't there, we would just be looking at a straight line. So the ax squared term is what makes it curvy. All right, so what does it mean to find the solution of a quadratic equation? We just talked about that. So you can go ahead and write that down again. Maybe you want to write it down in shorthand. What does it mean? I'll give it to you in real shorthand. You could say, to find the x-intercepts which make the equation true. That sounds all nice and casual, you know. You're at a math party, you're on a first date. They say, hey, what does it mean to solve a linear quadratic equation? and you're like, oh, let's find the x-intercepts, which make the equation true. And you can just throw it out there, real cash. Well, let's take a look at how many x-intercepts a parabola can have. How many x-intercepts could a parabola have? How many? It could be 2. If the parabola dips down below the x-axis, you're actually going to have 2 solutions. 2 solutions for x that x equals. But it's 2 different numbers you can plug into the equation to make the equation true. Or what if the parabola just barely sits on the x-axis? How many solutions do you have? 1. So that's only 1 number in the universe that you can plug into that equation and make it true. Right? And then what if the parabola is floating up above? There's no solutions. That means there's no number in the universe. There's no number from the number line. That's specific. There's no number on the number line that you could plug into that equation to make it true. And that's what we're really saying. And here, there's 2 numbers from the number line that you can plug into that equation to make it true. Here, there's 1 number on the number line that you can plug in to make it true. And here, there are no numbers from the number line that you can plug in to make it true. It might sound like a very subtle distinction, throwing in the phrase from the number line. But we want to be clear that we're just talking about the number line. When we talk about 2 solutions, 1 solution, no solutions. Okay. Finally, what is the quadratic formula? You all have it memorized from childhood? You hear it in your dreams? So the quadratic formula, x equals, is negative b plus or minus square root of b squared minus 4ac all over 2a. You remember that one?
Yes.
It's been a while since you've used it? Yeah. Well,
Not a fan.
you're not a fan? Well, hopefully this time around, meeting it, you'll feel a little better about it. Just to share something really cheesy with you, I have put this to music of Pop Goes the Weasel. And just to make sure it sticks in your head, I'll sing it. It goes, negative b plus or minus square root of b squared minus 4ac all. Yeah. I left it hanging there so your brain would have to fill it in. Yeah, so you could sing it if you wanted to. So anyway, there's the quadratic formula. And what is the b, a, and c that it's referring to? The a, b, and c from the quadratic equation. Note, again, subtle difference. This is the quadratic equation. Because it's an equation, it has an equal sign where you have 2 different sides to the equation. This is actually just a formula. And what is it telling you? What does this whole thing compute to? Like once you plug all those numbers in and you compute it, what is that telling you? Right, it's equaling to x, yeah. But specifically, what is that whole number once you compute it down to a number? Let's say it's 3. What is 3? The x-intercepts. Yeah, this is actually telling you the x-intercepts. The quadratic formula is a formula for x-intercepts. That's what it's telling you. Therefore, the quadratic formula is telling you the numbers you can plug into the equation to make it true. The quadratic formula is telling you the x-intercepts. Now, I'd like you to do this right here on this little drawing. You have enough space, I think. This is what makes the quadratic formula so cool. It has real meaning. At least I thought this was cool the first time I saw it. When you actually look at the graph for the parabola, this root and this root, this one, write this in on your side, is negative b plus the square root of b squared minus 4ac over 2a. And guess what this one is? Negative b minus the square root of b squared minus 4ac over 2a. See, we always memorize the formula as plus or minus. Right? That's just part of the formula. It's plus or minus. Negative b plus or minus the square root of b squared minus 4ac. The plus or minus is actually referring to the right x-intercept and the left x-intercept. The plus is the right x-intercept, and the minus is the left x-intercept. So it really is the location of the 2 different x-intercepts. We just combine them into one equation by saying plus or minus, but it's really telling you the right-hand one and the left hand. Okay, I think that covers the question, what does it mean? What does the quadratic formula mean? It's the x-intercepts of a parabola telling you the right one and the left one. All right, well, that's just a little introduction into quadratics. Well, let's go ahead and turn the page. We just spent a bit of time simplifying roots in the last chapter, didn't we? So I don't think we need to do much on this page other than just reminding ourselves, how do you simplify a root? Like, let's do the square root of 192. What is the square root of 192? Or better yet, how do we find it? I mean, I suppose there's a lot of different ways you can do it. Some of you might do a factor tree and then do the grouping technique. If it's me, I would have my square numbers written out, 1, 4, 9, 6. And then I would go to half of that number, which is like 98, 96 maybe. So I'd start at 96 and I'd start dividing, and oh, I already found it, 81 goes into that. So I would say that's really 81 times 2, which is really root 81 times root 2, which is really 9 root 2. Maybe you prefer the factor tree method. If you do, that's fine. You could split that up into 2 times 81, which is 9 times 9. And honestly, you could stop there because that means the square root of 192 is equal to the square root of 2 times 9 times 9. Since I have a pair of 9s, I can bring those out and call it 9 root 2. So either way, whatever method you prefer, we will continue simplifying roots throughout this chapter and for the rest of your lives. Okay, so that's it there. Let's look at this historical interlude. This historical interlude is very important. Long, long ago, humans didn't have a concept for negative numbers. Right? They did not have a concept for negative numbers. If you walked up to like a cave person and you're like, what's 5 minus 9? They would have told you it didn't make any sense. Now, obviously, we have a concept for negative numbers, so it's tough to empathize with them because you're like, 5 minus 9 is negative 4. What's the big deal? But imagine if you're just a caveman who's herding sheep, and you have 5 sheep, and someone comes over to you and says, hey, you owe me 9 sheep. Like, tough. Only got 5 sheep. I can't give you 9 sheep, right? So that's how they would have thought about it. The 5 minus 9 doesn't even make sense. It's not a real question. It's imaginary. That's what they would have said. Long, long ago, humans would have said the question 5 minus 9 was imaginary because it didn't make any sense. You can't take 9 sheep away from 5. Okay? Then long ago, just long ago, humans didn't have a concept for a number that wasn't a fraction. So the number root 2 was considered by some people as sacrilegious because you couldn't express it as a fraction. So just as a for instance, the square root of 2 is really 1.414 something, 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 something. There are no 2 whole numbers in the universe that you can divide to exactly equal root 2. To some older mathematicians, that was uncomfortable. Like, what do you mean I can't find 2 whole numbers to divide to equal root 2? That should be possible. Like, just give me time. I'll just keep looking. Eventually, I'll find a whole number that I can divide by another whole number, and it will equal exactly root 2. But in fact, that's impossible. There are no 2 whole numbers in the universe that you can divide that exactly equals root 2. And so for those mathematicians also, the root 2 seemed like kind of like not a real thing. Like if you can't get a number by just dividing 2 numbers, I don't know what you're talking about. Okay, so finally, until recently, and I'd say around the 1500s, it was considered impossible to square root a negative number like the square root of negative 1. So that's what, well, I erased it, but that's what we just did a second ago. Is it possible to square root a negative number, folks? No, it is technically not. It technically does not satisfy the definition that you gave to the alien from another planet. You cannot square root a negative 1. It just doesn't work. Mathematicians simply said it did not make sense. Kind of like dividing by 0. Can you divide by 0? No, you can't divide by 0 either. So square rooting a negative 1 definitely was something that you can't do. And even to this day, you can't really do it. However, history shows us again that what was once considered impossible or imaginary is not really. And this is one of my favorite quotes by Captain Jean-Luc Picard from the Starship Enterprise. You know, Star Trek, The Next Generation, the best Star Trek there is. He says, something is only impossible until it isn't. I like that quote a lot. So, imaginary numbers are what we're going to talk about first. So we're going to turn the page. So, the most important theme from today is that we want all equations to have solutions. Right? That's what mathematicians decided upon hundreds of years ago. They said, hey, we want every equation to have a solution. And what that means is, no matter what equation I write down, I want to be able to plug something into it to make it true. Okay, does that make sense? Mathematicians all agree that any equation you can write down, we want to be able to find something to plug into that equation that will make it true. That's the baseline assumption. So we already know what a solution is. What is a solution? A number that you can plug in to make it true. So just jot that down. What is a solution? A number you can plug in to make the equation true. So this is what mathematicians said around the 1500s. They said, it seems like there's a lot of equations that we can't finish. But we'd really like every equation to have a solution. So let's just go ahead and say we can. So for instance, this is an example of a problem that does have a solution. So let's look at it. X squared minus 1 equals 0. Does it have a solution? Maybe you can solve it in your head. What number can I plug in for x that will make it true? 1 or -1. Well, there's two different possibilities. Let's show it algebraically, folks. How do we solve for this with algebra? X is being squared and subtracted by 1, so we add 1. That gives us x squared. Really important that you do this with me, because we're about to do another problem just like it, but it's totally different. So we add 1 over, and then we square root both sides. And when you square root a square, it cancels out. So now it's just x equals plus or minus 1. And of course, what that really means is x equals 1, and it equals -1. Now, how do we know that that really is the solution? What do? We plug it back in. So let's do it. If I take something squared minus 1, I'm going to write it twice. Something squared minus 1. I expect that if I plug those objects in, it will make that equation true. So let's try it. Let's plug in 1. This is what it means for a solution to be a solution, is that you can plug it in, and it makes it true. So 1 squared is 1. 1 minus 1 is 0. So, yes. 1 is a solution because it makes the original equation true. That's what we even mean by the word solution. Now, how about -1? I plug in -1. Well, -1 times -1 is still positive 1, and 1 minus 1 is still 0. So that's all. So, what we see here is just a concrete example of what we mean by solution. A solution is only a solution because if you take it and plug it into the equation, it makes it true. So what about the next one? What is the solution to that equation? So this is the one that we all want to write down together for sure. X squared plus 1 equals 0. What number can you plug in to make that equation true? Well, I don't know, but let's go ahead and solve it with algebra. X is being squared and added by 1, so we subtract by 1. And then x is being squared, so we square root. That cancels the square. And it turns out that it's plus or minus the square root of -1. And so I could list that out. X equals positive square root of -1, or x equals the negative square root of -1. Now, if you were a mathematician more than a few hundred years ago, you would look at that, and what might you call that solution? You might call those solutions extraneous. You're like, hey, I know that the algebra told me that's the answer, but you can't actually square root -1, so that's impossible, so it's extraneous, so there's no solution. That's what you would have said. Extraneous, no solution. However, again, around maybe the 1500s, mathematicians said, no, I really want there to be a solution. I really want to have an object that I can hold in my hand and plug into that formula and make it true. Right? That's what I want. I want an object that I can plug into that equation to make it true. So then finally, a mathematician just said, well, let's try it anyway. I mean, I realize that that's silly and it's extraneous, but let's just go ahead and plug the square root of -1 into that formula anyway. Go ahead, everybody. Write it blank, write it empty, and let's go ahead and plug in the square root of -1 anyway. So again, imagine this is what really happened a few hundred years ago. Someone was just like, I'm going to do it anyway. I'm just going to plug it in. So what happens? You square a square root, what happens? It cancels, and negative 1 plus 1? It is true. This was really important in a shifting in how they thought, okay? This thing, if you look at it by itself, you'd say, that's impossible, it's extraneous, it's silly. But does it make the equation true? Yeah, it actually does make the equation true. And so based on that alone, they said, all right, listen, I know I can't square root the negative 1 because the square root of negative 1 is not on the number line. There's nowhere on the number line where I could put a dot and be like, ha ha, there's the square root of negative 1. Like, no, it's not on the number line. But regardless of the fact that it's not on the number line, what does it have the power to do? It has the power to make an equation true. And so based on that, mathematicians agreed to say the square root of negative 1 exists. Even though it's not on the number line, right? Even though it's not on the number line, this object has the power to make equations true. And if you have the power to make an equation true, we're going to call you a number. You're just not a number on the traditional number line, okay? Let's try the other one, by the way. Does negative square root of negative 1 make the equation true? So negative square root of negative 1 squared plus 1. Does that make the equation true as well? It might be helpful to write it times itself. So this is negative root negative 1 times negative root negative 1 plus 1 equals 0. First of all, what's a negative times a negative? The one, mind you, the one outside. The one outside is a negative times a negative. So that's positive. So what we really have is root negative 1 squared. Because the negative root negative 1 times negative root negative 1 really makes just the root negative 1 times itself twice. And that ends up giving us the exact same solution. And so yes, negative root negative 1 exists also. It exists by virtue of its ability to make equations true. So I want you to appreciate how weird that must have been in the 1500s. That a mathematician wrote all of his other mathematician buddies via Twitter. And he was like, hey, you know that square root of negative 1 thing? I think we should go ahead and call it a number because it can make equations true. Let's roll with it. Okay? That's what they did. So where are we at then? We've got the fact that the square root of negative 1 has the power to make equations true, so we'll go ahead and call it a number. So does the value square root of negative 1 have any true meaning? Put a big no right there. No. It definitely doesn't have any true meaning because you can't square root a negative number. So conceptually, recall the meaning of 4. The square root of 4 is 2 because 2 squared is 4. And the square root of 4 is negative 2 because negative 2 squared is 4. Right? That's what a square root means. That's the definition of a square root. Whereas if you tried to claim what the square root of negative 1 was equal to, you would have nothing to say. You wouldn't be able to finish that sentence. Because any number that you claimed to put here, you would have to write because that thing squared is negative 1, but there is no number that you can square to make it negative. As we've already seen, a positive times a positive positive, and a negative times a negative is positive. So is there any true meaning to the square root of negative 1? No. So mathematicians give the square root of negative 1 meaning by calling it imaginary. We use the word imaginary, we use the word complex, and really the sentence I want you to write right here underneath mathematicians, I want you to write down root of negative 1 has no meaning. But it can make equations true. That's kind of a big deal. And that's why we use the square root of -1 in mathematics, because what we're more interested in is making equations true, and we're less interested in actually finding the location of that object on a number line. So we're more interested in making equations true and less interested in, well, where is the square root of -1? It doesn't seem to exist. We don't care. We're just happy that it makes equations true. So we all agree to define I is equal to the square root of -1. That's our imaginary unit. So ever since, say, the 1500s or so, mathematicians have agreed to work with the letter I to represent the square root of -1. And we go ahead and use it in our calculations because some solutions go that way with a square root of a negative number. And technically, if you plug it into the equation, it will make it true. So we go ahead and call it the solution. How do y'all feel about that? That the square root of -1 is meaningless, but it makes equations true. So we use it anyway. Is it reasonable or unreasonable or weird or okay? Anyone have any opinions about it? After all, go back to the definition of what it means to solve something. What does it mean to solve something? Yeah, I mean, this is the primary definition right here. Does this definition say anything about whether or not that thing is actually a number? Well, I mean, I guess, yeah, to find the numbers that plug in to make it true. Yeah, we're saying it's a number. But yeah, all we want is just to be able to make the equation true. Okay, well, probably we're done, which also means what? What happens if you square both sides, folks? Go ahead and write down I equals root -1 and square both sides. What happens when you square both sides? You get I squared is equal to -1. That's the other fact. We're going to use those two facts over and over for the rest of chapter 10. So for the rest of chapter 10, we need to remember that I represents the square root of -1, which is not real, but it has the power to make equations true. And I squared is equal to -1, which is the one thing we said could never happen when you square a number. When you square a number, it has to be positive. And yet I, this mysterious beast, when you square it, it's a negative. Okay. Well, mathematicians agreed to treat I as a real thing so that they could go about normal everyday life doing computations that they otherwise couldn't do. So previously, what would we have said the answer was to all those problems?
Undefined or no solution?
Yeah, we would have said undefined or no solution. All of those, we would have just scratched them all out and said there's no answer, right? Undefined. In fact, there was a quiz question where the answer was undefined. I think it was a test question. Whereas now we are going to define it. We're going to define the square root of -1 to be I. So here's how we do these, folks. I'll do a couple with you, and then you can do it. The square root of -4. We're going to use the technique that I showed you previously about simplifying roots. So the square root of -4, I can actually split that into 4 times -1. Right? I just shave off the -1. Right? I just separate it as a different unit. And now I can use the product rule for roots to say that's actually root 4 times root -1. So you can see I just completely isolated the square root of -1. So now I have a real root and an imaginary root. And the square root of 4 I know is 2. And the square root of -1 I know is I. So the answer is actually 2I. Go ahead and do the next 2 problems, but not the last one. Do the next 2 problems just like that. Just like that. I want you to take root -25, split it into 25 times -1, split it into root 25 times root 1, and then write down your final answer. Okay, do that to the next one, but not the last one. So we did it this way so that you could see clearly why the square root of negative 25 is equal to 5i. But I won't require you to show this work every single time. From now on, you can just know, like the square root of negative 100, you can just know that anytime you see a negative under a square root sign, you can pull the negative out as an I. So I can, and you can, just immediately say, oh, the square root of negative 100, you mean I root 100? But you can just pull it out. Because you just know by definition that if it's a negative square root, that really represents an I. And then you can do the rest of the root formally. The square root of 100 is 10, so that's I times 10, but we write the answer as 10. I always goes at the end just like a variable. Like if you were going to say 10x or 10y, it goes at the end. So in the last one, root negative 121, again, you can just pull that negative out as an I. You just want to be careful not to put the I after the square root. Like perhaps you would have been tempted to write root 121 I. Because you know the I is going at the end, why not just put it there? Well, this could be confusing. Are you square rooting 121i? Like, does that go all the way over the I as well? Or does it not go over the I? It's kind of hard to tell. Some people put a little dip at the end of their square root to tell their audience that that's where the square root ends. And so this is really the square root of 101 times I. But textbooks don't really do that. And so the solution is to always put the I in front of a square root. So you put an I in front of a square root, but if you can calculate the square root to be 11, you put the I after a whole number. I'm just kind of telling you the formalism behind it. All right. So how about all of those square roots were perfect squares? What about a number that's not a perfect square? How do we simplify root negative 12? Please do the full solution with me. Root negative 12, you would again split that up as 12 times negative 1. But how can we split up 12? Yeah, it's really 3 times 4. Oh, actually, here. Remember our old strategy. Oh, there's my square numbers. What square number goes into 12? 4. So really what I'll do is I'll write down the square root of 4 times 3 times negative 1. I'm splitting it into its components. I'm saying, hey, 4 is a square number, 3 is not a square number, and the negative 1 represents the imaginary part. So now I can split that 3 ways, root 4, root 3, root negative 1, and that gives me the answer of 2, root 3, and an I. But we don't want to put the I after the root because that's confusing, so you put the I in between, like so. There's a whole hierarchy of how you express answers in math. A root normally goes at the end, an I doesn't go after the root, and an I goes after a number. All right, I didn't make this up, but that's how it'll be in the textbook. I's go after numbers, but before roots. So they end up going in the middle. So we'll just do one more of these. What would the square root of negative 50 be? Yeah, that would be 25 times 2 times negative 1. And then you can split that 3 ways into 3 different components. You'll have the square component, the non-square component, and the imaginary component. So you would end up with 5, an I, and a root 2. So go ahead and try one more. Maybe the square root of negative 200. All right, so for that last one, root negative 200, did you get 10 I root 2? 10 I root 2. Okay. Well, folks, this again is your introduction to imaginary numbers. Now, keep in mind, imaginary. We use the word imaginary because it's traditional, but do we still refer to negative numbers as imaginary? No, I mean, we think they're perfectly normal. You know, people thousands of years ago, they would have called it imaginary, but to us now it's totally normal. So in the future, will we continue to call these numbers imaginary? No. As society can, I mean, we've already had these numbers for 400 years. I don't know how long we have to wait before we just call them normal. But nowadays, we don't really call them imaginary, we call them complex. Complex is really the word that's used nowadays. They're complex numbers. Okay, so how do you compute with complex numbers or imaginary numbers? What do you think we should do with combining like terms? What's your guess? I mean, I have the answer written in the instructions, but I mean, what should we do? Well, yeah, the bottom one, yeah, we would FOIL. Well, what about the next couple? When you combine like terms, how do you combine like terms with I? Yeah, just like you would with any other variable. So it would be the exact same. If you have the problem 5 plus 8i plus 10 minus 2i, you'll just act as though I is a special variable. But it's still just a variable. You combine like terms. So 5 plus 10 is 15, and 8 minus 2i is 6i. So in that regard, I is just like any other normal variable. After all, technically, I is just a root. And as we've already said before, you can only combine like roots, right? Like I is actually the square root of -1. So I can combine my numbers together, and these are like roots, so I can combine those together. It's just that we're calling it I instead of a root. To save time, we use the letter I. Okay, how about FOIL? How are we going to do FOIL? Same way we always do FOIL. So everyone, let's do the middle one together. Let's do the middle one together. 10 minus 2i and 3 plus 5i. Let's do the whole process together. FOIL is first, so what's 10 times 3? 30. Outer was 10 times 5i, just 50i. What's inner, -2 times 3? -2i times 3. -6i. And then last, -2i times +5i. Is that -10i squared? It is. And just notice that that's the same answer we would have gotten if we had done 10 minus 2x times 3 plus 5x. It's the exact same answer. So first, outer, inner, last. It's the exact same answer. We're just using I instead of x. Okay, so now how do we finish simplifying this? We actually still have 2 more things to do. What's the first thing to do? If we combine like terms, we have 30 plus 44i minus 10i squared. But now we actually have 1 more thing to do. And that's the fact that I squared is a real number. I squared is a real number. It's just -1. Anytime you see an I squared, you can replace it with a -1. Even though I is imaginary, I squared is not. I squared is a real number. It's just the number -1. So we go ahead and replace I squared with -1. And so what does that give us? 30 plus 44i plus 10. And so we can combine like terms again. And we end up with 40 plus 44i. So what's the difference between doing arithmetic with I versus doing arithmetic with x? Nothing. Except that I squareds are equal to -1. So anytime you produce an I squared, you go ahead and replace it back out with -1. But otherwise, all of the computations are going to be the same. Isn't that weird? I've never thought about this. 0, 1, 2, -1, -2. I is not on the number line, but I squared is. How fun is that? There's I squared. Hello, I squared. You're right there, -1. But I is not on the number line. Just I squared is on the number line. All right, that's it for the warm-up. Folks, I don't know how I did. Would you now be able to tell someone what it means to solve a quadratic equation?
Yeah.
What does it mean to solve a quadratic equation, Vanessa? Yep. And what else does it mean, Lillian? To solve an equation? Or to solve a quadratic equation? Yeah, to get the x-intercepts. So what about the square root of -1? What is that thing? If somebody walked up to you, this would be an okay definition right here. If somebody came up to you and said, what is the square root of -1? What could you say, Daniel? But yeah, that's true, it's imaginary. Give me a little more. You can use that. But, yeah. So that's how you'd respond to somebody if they walked up off the street to you. They're like, hey, what's this deal with I equals the square root of -1. You can be like, oh yeah, sure, the square root of -1 doesn't have any real meaning. Your calculator will give you an error message. But if you plug it into equations, it can actually make the equation true. And that's why we deal with it. Okay. Gosh, this is a good stopping point, but we're not at our break yet, so I guess we'll just keep going. Here we are, chapter 10. It's all about quadratic equations. We're trying to solve quadratics. And the fact is, we're looking for numbers to make equations true. Sometimes it's going to be a real number. Sometimes it's going to be an I. All right? So sometimes when you solve a quadratic, the answer is a number. Sometimes when you solve a quadratic, the answer involves I. We will treat them both as real solutions. They are actual solutions to the problem because they make the equation true. We're just keeping this little mental distinction that I is an imaginary number and anything else is a real number. So everyone go ahead and just solve those first 3 problems. They're all basic algebra. You can all do it. There's no trick question here. You're absolutely right. But your answer is that. But I don't see that. How do you actually do that? I don't know. I was going to do it on next class. Wait, did I? When did I put it up? Oh, it's not even real copies. Somebody, I don't know. Yeah, I'll email it to you. What's that? Yeah, we do need that. We do need that. Sorry, I thought I had waited to give it out, but no, I didn't. We just went out. Okay, I'm just going to do that third one with you because the third one is a little more fancy than the previous two. How do I solve 8z squared minus 800 equals 0? Yeah, we add the 800 over to the other side because technically in order of algebra, in order of PEMDAS, z is being squared, multiplied by 8, and subtracted by 800. So you do the opposite of the last thing you say, so you add the 800 over. And then you have 8z squared equals 800. Yep, and then divide by 8. And so z squared equals 100. And then you square root both sides. And let's remember, anytime you do a square root in the process of algebra, you do have 2 answers. It's plus or minus. It is plus or minus. How do we really know that this whole plus or minus thing is real and not just some gimmick that we make up?
Well, tell us that it works and it seems to work.
There we go, because Mr. G says so, right? Well, how do we really know that we should put that plus or minus, and it's not just some sort of like cheeky whatever? Yeah, we put it there, but it's not real. Anyone have a thought? Is that real, or is it just something that we kind of do? It is real. Now I wonder how we could prove it to ourselves. Look at the equation 8z squared minus 800. Is there another way to solve that problem besides what we just did? Just look at this part. Forget about the equals 0. Look over here. What can you do? Vector what up? What can I take out? I can take out an 8. And then what can I do? You could divide off the 8. I'm just going to leave it there for a second. But that's fine. You can divide off the 8. How do I factor z squared minus 100? Yeah, difference of squares, z plus 10, z minus 10. And therefore, I've got the zero product rule. This times this equals 0. So one of those, or all of them, should be 0. Obviously, 8 can't equal 0, so that's meaningless. But z plus 10 could equal 0 if z were negative 10. And z minus 10 could equal 0 if z were equal to 10. And there's our plus or minus 10. So this isn't just some cheeky thing that we do just for fun. It really does represent the fact that there are two different numbers that you can plug into that equation to make it true. Okay, so let's keep going. How about that? How about when you're squaring a binomial? Then what do you do? Maybe let's ask what you shouldn't do. For that x plus 8 squared equals 9, what shouldn't we do? What shouldn't we do? FOIL. Oh, FOIL would be a big pain in the butt. If we FOILed that out right now, then we'd have x squared plus 64. No. We'd have x squared plus 16x plus 64 equals 9. And now our equation is worse. We'd have to bring the 9 over. Then we'd have x squared plus 16x plus 55. And then we'd have to factor that probably into like x, what, plus 5, x plus 11. And then we could probably, and then finally say that x equals negative 5 or x equals negative 11. So when you have a binomial being squared, your goal is not to FOIL it. Not always. Sometimes it is, sometimes it isn't. But in this case, what could we do that would be so much easier? What do we do? Yeah, we can just square root both sides. Way easier. X plus 8 equals plus or minus 3. Now I'd like to introduce a notation now. Okay? The notation is that when you have a plus or minus term and you're about to move more terms over to be with it, you always put the plus or minus at the end. So let's go ahead and move the 8 over very carefully. And our answer is 8 equals negative 8 plus or minus 3. Whenever you have a plus or minus, you put that number at the end and anything else in front of it. Now, in this particular case, we could go ahead and finish this problem. So what we'll do, and I hope you do this with me, this is how I will do all my problems on the board. I'm going to draw 2 arrows representing the alternate realities of this problem. On the one hand, it could be negative 8 plus 3. On the other hand, it could be negative 8 minus 3. So I'm using those arrows to represent alternate realities of this computation. Do any of you ever race your alternate reality home? Like you're in your car, and you're heading towards a red light, and you're heading towards a light, and you just miss it. And you have to stop. And you're like, oh man, if only I had made that light, where would I be now? I would get home like 5 minutes sooner. I'd be eating crackers 5 minutes sooner. Like, do you ever think about your alternate reality? I do. Anyway, that's what this is. I'm looking at the alternate reality of this computation. It was either the plus or the minus. And so our answer is negative 5 or negative 11. Is that the same answer we got the other way? Yeah. Both solutions are perfectly valid. But this is how we're going to be solving our problems for the rest of chapter 11. So let's try that one more time. This next one is a little more complex. It's 7s plus 6. I realize my phone went off. Let's just finish this. Yeah. So 7s plus 6 squared equals 16. So we definitely would not FOIL that. We would square root both sides. 7s plus 6 equals plus or minus 4. And this is the part where we want to be careful. When we move the 6 over, you put the 6 in front and the plus or minus 4 at the end. And then when you divide by 7, the whole thing gets divided by 7. So we have S equals -6 plus or minus 4 all over 7. Now here again, all of these are whole numbers, so we can compute them. But again, we will draw our 2 different arrows to represent the alternate realities of this problem. It could be -6 plus 4 over 7. It could be -6 minus 4 over 7. Those are the 2 different possibilities for this solution. And so it's either -2/7 or it's -10/7. And those are our 2 different answers. Okay, now by the way, what are these numbers? Well, that's true, the fractions. On a graph, what are these numbers? The x-intercepts. And what do these powers, or what do these numbers have the power to do? Make the equation true. So I want you to always think that in the back of your mind. These are x-intercepts, and they have the power to make that equation true. These are x-intercepts, and they have the power to make this equation true. And that's what we're doing. All right, thanks, folks. That's big break. It's 1:43, so let's be back at 1:50. Good. Oh, have I done this before? Because I don't have a strong memory of this. So where am I? Am any of these? And student has attended class. I think most of the time. Have you not missed a single class? Where do you go? Should I check that? I like this one. But no, but should I put a note? Good, but not by math. Use personal statements. No, it's not necessary. Okay, that one. I shouldn't put by math standards. No. Okay, I'll leave it blank. Incomplete math. That's a joke. So we should consider this one. Oh, you're good. Good. In what context? Yeah. Have you ever gotten that's a stick? Oh, I know a lot of people who have tried and they've been successful. They've actually gotten the point of it to actually in this year. Not this year. I don't think it would go right. But that is remarkable self. Okay. And okay, I don't know my phone number. My gateway number. It is 18. Oh, and it is 18. Yeah, oh, okay, there we go. Did I fill that out? Okay. I just made it up. I don't even know if it's a real word. Gosh, I hope I used it correctly. Oh yeah, it works. Yes, I used the word correctly. Okay, this is the reason. Yeah, I could. It's not black. It's not black. Yeah. But yeah. Don, any questions?
I'm still focused.
All right. Deacon, I tried to sip it. It was pretty good.
I know of some.
All right, so moving forward here, we're on number 6, and it says find the complex solutions to these equations. So there's just one subtle difference here. We're going to solve these using the same methods that we would use. It's just that when we get to the very end, our answer is going to be square rooting a negative number. But that's fine. When you square root a negative number, you just pull out the I, and your answer will be written in terms of I. So let's try the first one. X squared equals negative 144. So again, it's asking what number can I plug in to make this equation true? So we would square root both sides, giving us x equals plus or minus the square root of negative 144. And as we practiced in our warm-up, you can separate the negative from the 144. And so the square root of 144 is 12. And since it's negative, it's just 12i. So x equals plus or minus 12i. Now you can feel free to show all the work for that. All right, so if you wanted to, you can do root negative 144 is root 144 times root negative 1, which is 12 times I. You know, feel free to show work, but also feel free to just write it down. Right? Because we know that square rooting a negative means you're going to have an I, and then you square root the rest of it like normal. So what does this really mean? We're just going to do this once. X equals 12i or negative 12i. Those are the two numbers you can plug into that equation to make it true. So let's check. I want to know, is x squared equals negative 144 true when I plug in those numbers? Because that's the whole purpose of imaginary numbers, is they have the power to make equations true. So if I plug in 12i, what happens? You might write 12i times 12i twice. So 12i times 12i. What is that? You multiply the number times the number and the I times the I. So 12 times 12 is 144. And I times I is a squared. And what is I squared equal to? So in fact, it is true. If you plug 12i into that equation, it really does make the equation true, which is the whole point. I is not a real number. It does, however, have the power to make equations true, and that's why we use it. Same thing would go if we did negative 12i times negative 12i. We won't show that one, but it would do. So how about m squared equals negative 18? This is just slightly different. When you square root both sides, you have to go through the process of simplifying root negative 18. So what square number goes into 18? Is it 9? So 9 times 2 times negative 1. That's how you begin to split that up. So then you have root 9, root 2, root negative 1. Those are all being multiplied. And so that would give you plus or minus 3 root 2i. But we don't put the I at the end, we put the I in the middle, so it's 3i. So those are m is equal to. Now again, that's all well and good to say the answer is m equals plus or minus 3i root 2, but what does the answer mean? What can I do with those numbers? What can I do? Let's consider the positive one, 3i root 2 or negative 3i root 2. What can I do with that thing? Plug it in and make the equation true. I won't ask you to do it every single time because it starts to be laborious. But if I did square 3i root 2, then that would be 3i root 2 times 3i root 2. And then I can multiply them term by term. So 3 times root 2 times root 2 times I. And that would give me 9 times root 2 is 2. And I times I is I squared. And 9 times 2 is 18. And I squared is negative 1. So that's negative 1. So That's when we do these calculations and we end up with something in an I in it, I just want you to remember that the whole point of doing that is that you could then take that object, plug it back into the original equation, in this case, m squared equals -18, and you would actually get -18 out of that process. All right. So I'm going to leave number 8 for you. Let's do number 9. 9t minus 9 squared equals -10. Now again, at face value, folks, should this make sense that if you square a number, it would equal a negative number? Like, forget what's underneath my hand. If I square something, could it equal a negative? It shouldn't. Right? If you take something and multiply it by itself, it should end up being positive, but it ends up being negative, and that tells you already that this is going to be an imaginary answer. So, square root both sides. 9 minus 9 equals root -10. How do we rewrite root -10? You pull the negative out as an I, and so you just write I root 10. And so what we have now is 9t minus 9 equals I root 10. So finishing the algebra, oh, by the way, that's plus or minus. I didn't write that at first. It is plus or minus. Anytime you do a square root, it's plus or minus. So now we add 9 to the other side, as before. The plus or minus term goes second, so it's 9 plus or minus I root 10. Then we divide everything by 9. And that's our final answer. 9 plus or minus I root 10 over 9. Jasmine. Say that again, but louder.
Is that like
Right, very good. There's no point in doing alternate realities right now, because you can't add a 9 plus a root. So we just leave that as our final answer. Is that what you're saying? Oh. Yeah, folks, can you cross out the 9s? Can you simplify the 9s? Why not? And I really want you all to be very, very convinced by that. Yeah, the top is an addition problem. You can't cancel anything if it's an addition problem. You're only allowed to cancel things when it's a multiplication problem. Yeah. Yeah, you can't simplify root 10. No, it's not 2 root 5. What is the square root of 10? That's just root 2 times 5. There's not a pair of either one of those. So you can't bring anything out. And 10 is not divisible by a square number. Yeah. Good questions, Jasmine. Does that answer both of them? Okay. All right, so folks, that's the final answer. That's what it would look like. All right, so you're going to go back and try number 8. So we just have a couple cute word problems here. Now, folks, question. We just agreed to use the square root of -1 as a number because it makes equations true. Will the square root of -1 ever be an answer to a real life question? Like, could the square root of -1 be the length of a rectangle? Could it be the time it takes for something to hit the ground? No. In terms of word problems, an I would still be considered extraneous. In a real life world problem, I is still extraneous. It simply makes the equation true, but that doesn't mean it makes sense in the context of a real question. All right, so let's take a look at our first word problem there. It says, solve the given problem using Galileo's formula. You all know who Galileo was? Now, what is he known for? I think we all recognize the name Galileo, but gosh, what was he known for? Astronomy, yeah? What? Yeah, he was an inventor, yeah? Yeah, he very well could have popularized the use of telescopes to look at astronomical bodies. Like, he was the first one to use a telescope to look at the moon, I think. He also discovered some moons of Saturn. Yeah, he did a lot with astronomy. Okay, so it says Galileo's formula is what? D equals 16t squared. What on earth does that mean? Yeah, that's distance, and that's time. So under what context? What are we talking about? Driving? What else is Galileo known for? Gravity, what about? Yes, exactly right. Do you guys remember hearing any stories about Galileo standing at the top of a building and dropping things? So he would take things up to a building, and he would take things and drop them. And he would time how long it takes them to fall. So first of all, I just want you to imagine what a hard day's work that was. Right? People would see Galileo walking down the street. Hey, Galileo, where are you going? He's like, I'm off to work, dropping things. And you know what got him? What it got him? Eternal fame. Huh? That's not bad. Hey, how'd you get eternal fame? I dropped things. I drop things all the time. I'm not eternally famous. Galileo, he nailed it. So Galileo stood on top of tall buildings and dropped things and counted how long it took. Now, to be fair, something falling doesn't take very long for it to fall, and he didn't exactly have a stopwatch. So you know what he did instead? He put objects on a very slightly inclined plane and watched them roll to the bottom. Because that way it would take longer for an object to roll to the bottom, but it was still measuring gravity. It's just that he had more time to actually count. 1, 2, 3, 4. Whereas here, it's always like 1. You know, what kind of data can you get from that? Okay, so this formula is for something falling off a building. That's what D equals 16t squared means. The 16 is specific to Earth gravity. And what we're saying is, D is the distance the object falls, and T is the time it takes to fall that distance. So that's what this formula is. It's his formula because he came up with it first. So Eric has a tree house 28 feet above the ground. Folks, do you know how tall 28 feet is? That's like a pretty tall tree house, isn't it? 28 feet? That's like a 3-story building almost. Dear goodness, that is a really tall tree house, folks. All right, so he has a tree house, 28 feet. How long would it take Eric to hit the ground? Sorry. How long would it take a water balloon dropped from the tree house to fall to the ground? So how long will it take? Where do we plug in the 28? Yeah, for the D, because that's the distance, and we're solving for time. So that's it. You plug in 28 for D, because it's falling 28 feet. Then you divide off the 16. And what is that? 14/8, which is really 7/4. So we've got 7/4 equals T squared. And then what? Square both sides. So T equals, how do you square root a fraction again? You square root the top and the bottom. That's nice because that's just √7/2. Technically, that's a plus or minus. Does the minus matter? No, because time can't be negative. At least it doesn't make any sense for time to be negative. Now just imagine, does it make any sense for time to be negative? No. Does it make any sense for time to be imaginary? Whoa, what even does that mean? Negative time is one thing. Imaginary time? Those are two totally different concepts. It'd be worth reading about. You can read about it. All right. So you would type that into your calculator and you'd get an approximation. What did it turn out to be? Does anyone already have it? 1.3? Okay. So roughly 1.3 seconds for Eric to hit the ground. For Eric's water balloon to hit the ground. All right, how about this? A young boy is delighted to drop various objects from a hotel balcony to the ground below, etc., etc. You guys solved that one on your own. Let's keep going. Okay, interlude. Who did not get my other sheet of paper from the back of the room? Did anyone not get this one? Double it, square it. Jasmine? Are you the only one? Nick, did you get one? Eduardo, did you get one? Hmm? And her. Okay, so a few of you. You didn't get one either? Oh, I see. Okay. Oh, right. Okay. Okay, so in other words, there's a lot of you. Well, here's the thing. You don't even need the sheet of paper. All the problems are right up here on the board. So you can just write them down with me on a sheet of lined paper. Sorry I didn't bring it up. I thought I had enough photocopies. So you can just write this down on a sheet of lined paper if you don't have the paper. So what I'd like to do right now is just review a rule that I think we've already talked about. So this is actually going to be a very fast review. Yeah, I think we've done this before. So have you heard me say the double it, square it rule? I think we've talked about it before. Let's look at x plus 7 squared. I would like us to all be familiar and comfortable with a shortcut so that you can just write down the answer to this without doing FOIL. So let's look at what FOIL would look like. It would be x plus 7 times x plus 7. And you do the whole FOIL process, x squared plus outer 7x plus inner 7x plus last 49. And then you'd have to combine like terms and you get x squared plus 14x plus 14. Well, I don't want any of us to have to go through that process over and over again. You know, it's repetitive. If you can just memorize, where did the 14 come from? Well, you could say 7 plus 7 or 7 times 2. I call that double it. And where did the 49 come from? Square it. So that's it. That's the double it, square it rule. And I would like us all to be very familiar with that so that when you see problems like these, you can just write down the answer very quickly. No need to go all the way through the process of FOIL, combine like terms, etc. So I'll do a few with you. P plus 1. Just so you know, you always start by writing the variable squared, and then what? You take that number and you double it. So in this case, 1 times 2 would be 2. And then you square it. 1 squared is 1. And that's it. That's the double it, square it rule. You take the number inside the binomial, and you first double it, and then you square it. So how about v minus 7 squared? This one's a little tricky. Again, you begin with the variable squared, and then what's negative 7 doubled? Negative 14b. And then what's negative 7 squared? Plus 40. That's the double it, square it rule. What do you notice about the last number? What do you notice about the sign of the last number? It's always going to be positive. Always. Because anytime you square a number, it's positive. That is, anytime you square a number other than I, it's positive. What do you notice about the middle number? What do you notice about the sign of the middle number? It keeps the sign of the binomial. Yeah, if the binomial is positive, the middle number is positive. If the binomial is negative, the middle number is negative. So that's it. We don't even have to do any more from that. You could just practice a couple times for muscle memory, you know, just to feel good about it. So why don't you just go ahead and do a couple more. Here's b plus 7. Oh, no, we already did that one. How about n minus 2? That's a good one. N minus 2 squared, you begin by writing down the variable squared, and then you double the middle, or double the number, so negative 2 times 2 is negative 4. And then you square the number, negative 2 squared is 4. As I said, this is a shortcut. No, it's so rare that I advocate shortcuts because I like showing it works so much. But this, I believe, is a shortcut we can all benefit from. Being able to write it down quickly. I think that's all that I have on the front side. Let's flip it over. And what we wanted to do now is be able to go backwards. All of these trinomials are the result of the double it, square it rule. So given that, let's look at one together, folks. Let's look at this one together. Everyone, let's look at b squared minus 10p plus 25. How can I use the double it, square it rule to figure out what number was inside? I've got two choices, right? What can I do to the last one? Square root it. Well, what's the square root of 25? Plus or minus 5. Now, which one? I don't know. What's the other way I could do it? Take that one in, divide it by 2. That's the better one. Sure, you can square root the last number, but you don't know if it's plus or minus. But the middle one will tell you for sure. You take the middle number and divide it by 2. That is the number that's in the binomial square. So you can pretty quickly go through all of these, training your brain to just look at the middle number and dividing it by 2, and that will tell you what it should be. So for instance, I'll do a couple more from this side. N squared minus 6n plus 9. Squared minus 6n plus 9. Looking at this, I would just take the middle number, divide it by 2. That's negative 3. That's the answer. It's n minus 3 squared. So we're going to look at the middle term, not the last term. That's not reliable. The middle term is reliable. You take half of the middle term. Okay, but there's more I want to say about this. Do you know for sure that all of these are the result of a binomial being squared? Other than me telling you that they are, do you have any guarantee? We have no idea whether or not these are actually the result of a binomial being squared. So what I really want to talk to you about is a check mechanism. A check mechanism, I think we've done this before, a check mechanism to know if it is. So everyone, let's just start back up at number 12, k squared plus 8k plus 16. The check mechanism I'm about to show you, we're going to use it over and over. So I really want you to write this down with me. Here's what you do. You say, I wonder if this is the result of a binomial being squared. I wonder, can this be rewritten as k plus or minus something? I wonder. So here's what you do. You say, take the middle term and divide it by 2, which is 4. And then you square that number, which is 16. And then you look. Is that 16? And it is, so it is. This is the result of a binomial being squared. So what number goes inside the binomial? The 4. Have we done this before? Okay, well, good. That's great. Well, that's called the check mechanism, and we're going to use it quite a bit. So I don't know that there's anything else we need to do from this page. Oh, except for the bottom. Yeah, the bottom is going to tell us exactly, or it'll be a good practice. So looking at the bottom, we'll do the first few in a row together. I've given you a problem, y squared plus 26y plus c. They say find the value of c that completes the square and then factor it. So what they're saying is, what number would have to be there so that this could be written as y plus something squared? What's that? 169? No. These are all, I think you're on the right track, but now let's actually do it. The check mechanism will tell you. So everyone do it with me. The check mechanism says, take the middle number, divide it by 2, and then square it. And whatever that number is the number that should be right there. I really encourage you to show this the way I'm showing it. Arrow down, take the middle number, divide by 2, arrow, that's 13. Now square it, arrow, it's 169. That should be the number right there. So if it were y squared plus 26y plus 169, then you could rewrite it as y plus 13 squared. That's what we're saying. Saying use this check mechanism of take the middle number, divide it by 2, square it, and put it at the end. If that is the number at the end, then this trinomial can be rewritten as that binomial squared. That's the overall flow. Let's try a negative one. Let's try number 26. Y squared minus 30y plus c. So what number should be there for c? We take the negative 30, we divide it by 2, which is negative 15. We square it, which is 225. And that's the number we put in for c, 225. And then you say, If it were y squared minus 30y plus 225, then you could rewrite it as y minus 15 squared. Again, the number in the binomial is the number in the middle of the check process, the check mechanism. That's the number that actually goes in the binomial squared. Let's do one more. Is there one up there that looks trickier than others? One that you'd like to see done? I mean, I guess technically none of them are more tricky than the other because you just do the check mechanism and you're done. But which one would you like to see? How about number 25? M squared minus 16m plus something? That's number 25. So the check mechanism, arrow down, you take your middle number divided by 2, arrow right, that's -8, square it, arrow right, that's 64, arrow up. That's what the C value should be. And if the last number were 64, then I could rewrite it as m minus 8 squared. Now you might be asking, who cares? Like, what's the difference? Why does it matter if I can rewrite this as this? And I'll tell you right now, there's a huge difference. Watch, and you tell me which one you'd rather solve. Would you rather solve this equation, m squared minus 16m plus 64 equals 0? Or would you rather solve this equation, m minus 8 squared equals 0? Because they both represent the same equation, but which one's easier to solve? This one, right? Because what do? You just square root both sides. That takes care of the square. And then you just add the 8 over. Whereas, how do you solve this equation? Yeah, you have to factor it. You have to say, okay, 1 multiplies to make 64. That adds to make -16. That's -8, -8. Okay, so now I have m minus 8 times m minus 8. And I set it equal to 0. So by the product rule, either that's 0 or that's 0. So m minus 8 is equal to 0 or m minus 8 is equal to 0. So that means that m equals 8. Now you might say that both of them seem fine to you. You know, like, hey, whatever, I'll do either one. But I think technically this one is easier. It's definitely easier if that's not factorable, right? What if this wasn't factorable? How would you have to solve it? With the quadratic formula? And we haven't even done that yet. So definitely this is the way to go. And that's our strategy for the next section that we're going to talk about. So that was just a little interlude. Everybody go back and take a look at 10.2. Boy, I'm really glad that class doesn't get out at 2:20, it gets out at 2:50. We have a whole other half an hour. Do you know how excited I get when I realize we still have lots of time left? Sometimes like, oh no, we only have 5 more minutes. And then I'm like, oh, we have an hour. And then I get all excited. I'm sure that's how you all feel too, right? When you're like, oh no, we only have 5 more minutes. And you're like, oh, whew, thank goodness. We're still going to sit here for another hour. I imagine that's how you feel too. That's how I feel. So let's see how to complete the square. This is a really exciting process. Do any of you remember completing the square? Have you heard what? Okay, fantastic. You probably did it in high school. Not in any previous class. You don't do it in 120. No, this is 120. You do it in 120. You don't do it in 090 or anything like that. So it could be that it's been a while since you've done this. So we're going to start at the beginning. We're going to write down all of our steps so we know what to do. These first 2 questions are just asking for the skill we already did. It says, decide what number must be added to make it a perfect square trinomial. So what number would you have to add to the first one? Theoretically, you could do this in your head. Remember the check mechanism. You take the middle number, you divide it by 2, and then you square it. So the number is 81. Yeah, 81. I'm going to do that over here. So x squared plus 18x plus something. Again, I really hope you're all writing down this check mechanism. It's part of the process. So you take 18, you divide by 2, you get 9, you square it, you get 81. That's the number that goes there. And if it were 81, then what could you do? Rewrite it as x plus 9 squared. So how about the next one? Why is the next one a little more tricky? P squared plus 13p plus what? What number do we have there? What? 6 points? Well, it is a decimal. It's not 6.5 then. What's the check mechanism? Take the middle number, divide it by 2, which is 6.5, and then do what to it, Daniel? Square it. And 6.5 squared is? Yeah. 42.25? That's the number. There we go right there. And if it were, how could we factor this? P plus 6.5. Daniel, maybe that's the number you were telling me. Oh, okay. Yeah, you can factor it as P plus 6.5 squared. Now, we just did that as a decimal, and I'm sorry to say that for the rest of the problems, we're always going to keep it as a fraction. So let's try that again, but using a fraction. Okay, same problem. But we don't want a decimal, we want a fraction. So p squared plus 13p plus what? So you take the middle number, you divide it by 2, that's 13 halves. And then you square it, so 13 halves squared is 169 fourths. We'll want to keep fractions, not decimals. So that's the number that goes at the end, 169 fourths. And if it were, how could I factor it? It would be p plus 13 halves. Okay. I realize that's very subtly, it's very subtle. Over here we did it with decimals. Over there we did it with fractions. We're going to want to use fractions for the rest of this chapter. So that right there, that process is called completing the square. Completing the square because we're completing this expression so that it can be rewritten as a square. That's what completing the square means. We're finishing this expression so that it can be rewritten as a square. Okay. So this is our first example of completing the square as a full problem. So everybody, first of all, go ahead and rewrite it again in your own handwriting. A squared plus 12a plus 27. And going all the way back to the beginning of class, what is it we're trying to do? Find the numbers that you can plug in and make it true, which will be the x-intercepts. So let's cheat real quick and just find out what the answer is. It's x squared minus 12x plus 27 equals 0. And there's my parabola. Gosh. What did I do wrong? That was pretty wild. That's not even correct. X squared minus 12x plus 27 equals 0. Okay, maybe it is correct. I want to make it look like a real parabola. What is happening? X squared minus 12x plus 27. Isn't that the formula?
Yeah.
Where? You mean? That's it. Strangely enough, this is graphing two vertical lines. That doesn't make any sense. Oh, sorry, equals y. There we go. So there's my equation. Y equals all that. And so What are the x-intercepts? 3 and 9. So everyone go ahead and write down the answer. The answer is 3 and 9. We're going to check that we get that answer by the time we're done. But we know the answer is 3 and 9. Sometimes it's nice just to know where we're going so that we can check our answer when we get there. So I'd like to find the answer. I'd like to find the numbers I can plug in to make it true. Apparently it's 3 and 9. And I'd like to solve this problem using the technique called completing the square. So here we go, folks. Step 1. Oh, and I should clarify. This is ax squared plus bx plus c equals 0. And our equation is a squared minus 12x plus 27 equals 0. There we go. So the very first thing we want to do is just check. Is this already a perfect square? Does it work? Does this already have the relationship we want it to have? Let's take a look. Take the middle term, divide it by 2, square it. Is that a 36? No. So this thing cannot currently be rewritten as a square. What do I wish that number was? Yeah, I really wish that number was a 36. Okay, I really do. If that were a 36, I could factor this and then square root both sides and I'd be done. But it's not a 36, it's a 27. But I really wish it were a 36. So what could we do? Just keep that in mind. I really wish that were a 36. What could we do? What's that? Say that again. I'm an old man. I can't hear. If I had 6 of that, it would be 33. You could add 9 to both sides, folks. And that's fine. That would accomplish our goal. But there's a technical process that's normally done where the first thing we do is we just get rid of the 27. Just get rid of it. Move it over to the other side so it's gone. That way there is no number there. So step 1 is to move the number term to the right. Vanessa, what you said is absolutely correct. That would have worked. But this is the procedure that's typically done. I want to show you guys what's in the book. So step 1, move number right. Okay, that's what we just did. Now what we would do is add the number that we want to both sides. So what number do we really want to be right here? 36. So we'll go ahead and add it to both sides. So I add it here, and I add it here. So step 2, add special number. Special number to both sides. Now, first of all, what's negative 27 plus 36? 9. And that's what Vanessa was suggesting. If you just added 9 to both sides, we would have gotten to this and that. But this is the procedure they do. So what can I do with this part now? Now that it is a perfect square trinomial, I can rewrite it as what? Yeah, a minus 6 squared on the left. And then 9 on the right. So that's step 3. Rewrite / simplify. That is, you're rewriting the left-hand side and you're simplifying the right-hand side. Now, just so you know, folks, we're done with the process called completing the square. That was it. That thing that we just did right there is called completing the square. So when you see instructions on a test item or in a book and it says complete the square, that's what we just did. We took a trinomial that was not a perfect square binomial. We moved the number term to the right and then added the magic number we wish we had so that we could rewrite it as a perfect square. And that's the process called completing the square. This is the square that we just made. So this thing right here is the square we just completed. That's where the word comes from. Okay, so now how do we solve? Just basic algebra. Just square root both sides. So that's a minus 6 equals plus or minus 9. So that would be step 4. Square root both sides. Thank you.
That would be a 3.
And the rest is just algebra. So I'll write that down as the 5th step, algebra. You might have to do some more algebra to get to your answer. So we add the 6 over both sides. We end up with a equals 6 plus or minus 3. Again, the plus or minus number always goes at the end. And then we use arrows to explore our 2 different alternate realities. It's either 6 plus 3 is 9, or it's 6 minus 3, which is 3. And are those the x-intercepts that we saw originally on the graph? 3 and 9? It is. The x-intercepts we saw in the beginning was 3 and 9. So that methodology right there that we just did is called completing the square. Jesus. You did what? Ah, yeah. So what you just did there was factoring. And folks, we should talk about that. Jesus went ahead and used a strategy that we knew from the past. And I was wondering if some of you might just want to do it that way. What other way can we solve this problem? You can just do factoring. What multiplies to make 27 that has to make 12? Yeah, 9 and 3 if they're both negative. So this is really just a minus 9, a minus 3. And using the zero product rule, we get the answer of a equals 9 and a equals 3. Certainly this solution looks faster, right? And that's why Jesus was tempted to write it down. It is faster, but the fact is you can't always factor. Factoring only works when you can find 2 numbers that multiply to make this term but add to make this term. Not every quadratic expression is factorable. And so when an expression is not factorable, what method do you have to use? Completing the square. So that's why we practice it. So we will continue practicing completing the square right now. And so very important that you're practicing it with us and writing this down. Because on the take-home quiz that I give you, I will tell you which method I want you to use. I will say, solve this quadratic by factoring. Solve this quadratic by completing the square. Solve this quadratic by using the quadratic formula. So you have to use the method I tell you in order to earn credit. Okay, so here we go. Let's try another one. I hope you can see my steps. I just realized now that blue is not the darkest color, but those are the steps right there. So let's follow those same steps. We're going to write down z squared plus 12z plus 18. What's step 1? Yeah, move that number term to the right. Not the z squared term, not the z term, the number term. Just go ahead and move that number term over to the right. And leave some space. You want to write z squared plus 12z, leave some space, equals negative 18. Why do we leave space? Because we have to add our special number in there. So what's step 2? Add the special number. Now we don't know what the special number is yet. We have to do our check mechanism. So bring down the middle number, divide it by 2, take that number, square it, it's 36. That's the number that we add to both sides. So you do your little check mechanism real quick, find out what number you want to add to both sides. In this case, it's 36. The check mechanism gives you 2 things. The check mechanism tells you what number to add to both sides. The check mechanism also tells you how to rewrite your trinomial as a binomial squared. So really important that you show that work. I wouldn't just do that in your head. I would write that down so you have it. Now, step 3, Genesis. Rewrite the left-hand side as what? Yep, z plus 6 squared. And then what was the rest of step 3? Rewrite and simplify the right-hand side. So negative 18 plus 36 is it plus or minus 18? Deegan? Why not? Yeah, we didn't square root it yet. Yeah. But Deegan, what's step 4? Square both sides. So we square both sides. Now we have z plus 6 equals the square root of 18. So we know the answer is plus or minus. What is the square root of 18? You probably want to go somewhere else and do some scratch work. So root 18, what square number goes into it? 9. So that's root 9 root 2, which is 3 root 2. So that's our answer is 3 root 2. So z plus 6 is equal to the square root, I'm sorry, equal to plus or minus 3 root 2. And the last step? Yeah, just basic algebra. Finish solving for your variable. All the hard stuff is done. Z equals negative 6 plus or minus 3 root 2. Are there alternate realities here? Yeah, you're either going to do negative 6 plus 3 root 2 or negative 6 minus 3 root 2. But you can't actually combine 6 with a 3 root 2. So, I mean, if you wanted to, you could write down negative 6 plus 3 root 2 and negative 6 minus 3 root 2. But the fact is, you can't actually add those together. So we're just as well just leaving it like this. If you were going to write out those two different alternate realities, you would want to type it into your calculator and get an actual decimal. That you could do. I could type in negative 6 plus 3 root 2 and negative 6 minus 3 root 2. And I could get two decimals. I could say the answer is negative 1.75 or negative 10.24. But those are just decimal approximations. And you know what a decimal approximation is, right? A lie. Right? The answer is not really 1.75 and the answer is not really 10.24. There's a lot of decimals there that I just cut off. So again, this is your best answer. Negative 6 plus or minus 3 root 2. All right, that process is called completing the square. Hey, Jesus, can you factor that one? Yeah, no, that one doesn't factor. You could try. You could say what multiplies to make 18 that adds to make 12, but you would quickly see that there is nothing that multiplies to make 18 that adds to make 12. And that's why we have to do completing the square. Now, the next one, what looks tricky about the next one? Yeah, the next one is a fraction. Why is it a fraction? What about this is going to turn into a fraction? The middle term. You always take the middle term and divide it by 2. So you could say 3 divided by 2 is 1.5, but we want to keep the decimals. So let's try this again. P squared was 3p minus 9. What? It's step 1. How do you have it? Yep, move the 9 over. So now we have p squared plus 3p, make a space, equals 9. And what's step 2, Jackie? Yeah, we're going to do the check mechanism. What I have written up there is add the special number to both sides, but you're right, we have to find the special number. So I'm going to take my middle number divided by 2, which I'm going to keep as 3 halves. I'm sorry, then what, Jackie? Yep, square it so you get 9/4, and that's what you add to both sides. 9/4. The left-hand side is actually easier to do now. I mean, between the two sides. What's step 3? Yeah, we're just going to rewrite and simplify. So how do I rewrite my trinomial as a binomial squared? It's p plus the 3 halves, because that's the number in the middle, p plus 3 halves. Now, what about the right-hand side? Now, the right-hand side, you folks can feel free to do that however you wish, so long as you give me an answer that's a decimal. I'm sorry, I said that completely wrong. So long as you give me an answer that's a fraction. So you could do all the work of writing down 9 plus 9/4 is really 9/1 plus 9/4. Find a common denominator of 4, so that's 36/4 plus 9/4. And so that's 45/4. If you want to do all that work, you know, kind of on the scratch work side of your paper, that's just fine. And the answer is 45/4. Or what can you do with your fancy calculators? You can type in 9 plus 9/4, hit enter, gives you a decimal. But then what do? Some of you, there's a button on your calculator that says math. Everyone find that button, math. If you hit the math button, what's the very first option? Frac, for fraction, you hit enter, enter. And it tells you the answer is 45/4. Okay, that's fine. You can do that. So everyone who has that option, you can do that. For those of you with scientific calculators, you also have that option available to you. Yeah, FD. So for instance, Deegan here, he has the wait, where's your option? Oh, there it is, FD. So it's F arrow D, and that'll turn a number between a fraction and a decimal. So I guess my point is, folks, we have calculators to do fraction work for us. There's no real need for us to do that. So if you want to use a calculator, that's fine. So what's the answer? 45/4. Okay, next step, step 4. Square root both sides. And how do you square root a fraction? Yeah, top and bottom separately. So that would be root 45 over root 4, which is really what over 2? Can root 45 be simplified? I don't have my square numbers on the board anymore. But is there a square number that goes into 45? 9. Now 9 does. So that's really root 9 times root 5. So that's really 3 root 5 over 2. So that's what the right-hand side equals, plus or minus 3 root 5 over 2. Now, folks, to be honest with you, this process right here is normally a game stopper for a lot of people, right? They hit this part, and they get all frustrated, or, you know, oh, man, now what? Oh, no, I have to simplify. Oh, no, and then they stop, right? So push through. Push through. Like, there's a lot of little computations along the way we have to do. After all, we just had to do 9 plus 9/4, right? So you had to find a common denominator, get that, and now you have this whole simplification process to do, but it's just part of the problem. So again, scratch work might be the way to go, to just go somewhere else, do the scratch work, and then come back and put in the plus or minus 3 root 5 over 2. All right, finally, step 5, do algebra, subtract the 3/2 over. This part's kind of tricky, everyone watch carefully. We're now going to write down P equals -3/2 plus or minus 3 root 5 over 2. Again, because the plus or minus goes at the end. Now, what's the last thing we could do to clean this up?
An alternate reality.
We could, but we don't have to because it's a root. And so we can't actually add them or subtract them together, although we could get a decimal. The last thing we could do, what do you notice about our denominator? It's the same. So we can go ahead and add them together. -3 plus or minus 3 root 5 all over 2. Now, folks, what do you notice about this answer? Does it evoke anything? Do you look at it and you're like, hey, that looks a lot like right. It does look a lot like that. It looks a lot like that because it is it. The quadratic formula gives the same answer that the completing the square gives as well. The quadratic formula is just a general formula that gives you the answer for completing the square. So given that, just off the top of your head, what would you rather do? The quadratic formula or completing the square? I mean, maybe you prefer completing the square. Maybe you're like, forget completing the square. I'm just going to use the quadratic formula. After all, they're giving you the exact same answer. And so that's what we'll get to next time. Now, folks, So next week, when Larry Dieter comes in, you all let him know to start on number 17. I'll let him know as well that you're starting on number 17, and then you're moving forward doing the quadratic formula and more problems. And you guys will get as far as you can with Larry on those 2 days. Okay, I think I have something to give back to you, or maybe I don't. Do I have anything to give you? I don't know. Here, folks, I should give you your midway quiz. Because, let's see here. The midway quiz. The first 3 problems are just algebra. On the back, it says solve by completing the square. And at the bottom, it says solve by using the quadratic formula. So you guys are all ready to do problems 1, 2, 3, and 4. And on Monday, Larry will do the quadratic formula with you, so then you can do this one. And I think what I'll have him do is collect this from you on Wednesday. Okay, so I'm giving it to you now, and I'm telling you now, it's due Wednesday, a week from today. Okay, now, as far as the quiz goes, friendly reminder that you can use your notes, and you can use your textbook, and you can even use my math lab, because my math lab is your textbook. But you cannot use Google, and you cannot use another human. This is only for you to do on your own. However, if you reach a tricky point, and you're not quite sure what to do, you can always email me, right? And then maybe I would be able to direct you to a good place for help. I just had a student earlier today email me about a question on a midway quiz, and I replied by telling him which problem we did in the notes, that was like the problem on the quiz. And that's just fine. I'll just remind you where to look in your notes. All right, thank you, folks.